Hey guys, welcome back to the laboratory. In this video, we are looking at rates of reaction. By the end of this video, you should be able to define what is meant by rate of reaction, describe how the rate of reaction can be measured, and use graphs to explain the rate of a reaction. So, let's go. During a chemical reaction, the reactants, the substances found at the start of a chemical reaction, react with one another to form the products, the substances found at the end of a chemical reaction. The rate of reaction is a measure of the speed at which these reactants turn into the products. For example, the rusting of iron is a chemical reaction that takes several years to occur, and is therefore a reaction with a very slow rate. In contrast, explosions such as fireworks are chemical reactions that take place in mere seconds, and are therefore reactions with a very fast rate. The rate of reaction can be measured in two ways, the first of which is to measure how quickly the products are formed. This graph shows the typical trends observed when measuring how quickly the products are formed during a chemical reaction. At point A, this steep line indicates that at the start of the reaction, the rate of reaction is very fast. This is explained by the high concentration of reactants at the start of the chemical reaction. The high concentration of reactants increases the likelihood of successful collisions between reactant particles, and so the rate of reaction is much faster. At point B, we see the line begin to level off. At this stage, the rate at which our products are formed begins to slow. This is explained by the fact that our reactants are now being used up. And at point C, we see the line is completely flat. At this stage, the reaction has stopped as the reactants have been completely used up. Therefore, the concentration of the products does not change. The second way of measuring the rate of a reaction is to measure how quickly the reactants are used up. The trends on this graph are identical to those observed on the previous, only this time they are reversed. So, at point A, this steep line indicates that the rate of the reaction at the start of the reaction is very fast. The high concentration of reactants at the start of the reaction means successful collisions are happening more frequently. Therefore, the reactants are being used up quickly here. At point B, we see the line begin to level off. At this stage, the concentration of the reactants has fallen significantly, and so successful collisions between the reactant particles become less frequent, slowing the rate at which the reactants are used up. And at point C, we see the line is completely flat. Here, the reactants have been completely used up, and the reaction has therefore come to an end. In practice, we would monitor the rate of a reaction by measuring changes in the mass or volume of reactants or products. In a reaction that produces a gas, we can use a gas syringe to measure the rate at which the gas is produced, and thus the rate of the reaction. For example, the chemical reaction between magnesium and sulfuric acid produces magnesium sulfate and hydrogen gas. To measure the rate at which the hydrogen is produced, we can use the apparatus pictured here. To achieve accurate results, it's important that the system is closed to prevent any gas from escaping, hence the presence of the rubber bung. The reaction takes place in the conical flask, and the hydrogen gas will rise and move into the gas syringe. The faster the syringe moves, the faster the reaction. Once the syringe stops moving, we know that the reaction has come to an end. In contrast, if a reaction produces a gas, then we can also use a scale to measure the change in mass as the gas escapes. For example, the reaction between calcium carbonate and hydrochloric acid produces calcium chloride, carbon dioxide, and water. To measure the rate at which the carbon dioxide is lost, we can use the apparatus pictured here. Cotton wool is placed at the mouth of the conical flask to prevent acid spray, which would impact the accuracy of the results. However, the carbon dioxide is still able to escape. As the reaction takes place, the carbon dioxide will escape and the reading on the scale will decrease. The faster the loss in mass, the faster the reaction. Once the reading halts, we know that the reaction has come to an end. Here's an example of a past paper question that I'd like for you to attempt to test your understanding of the content covered in this video. Pause the video and take your time to work it through. Press play once you're ready to check your answers. When copper carbonate reacts with sulfuric acid, carbon dioxide gas is formed. Explain how an electric balance could be used to investigate the rate of this reaction. As always, the information given in this question is telling, and it's very important we pay close attention to this. We are told that in the reaction between copper carbonate and sulfuric acid, carbon dioxide gas is formed. Therefore, we know we are going to be investigating a loss in mass. Our first mark is awarded for stating that we can use the scale to measure the change in mass of the reactants. And our second mark is awarded for stating that the faster the loss in mass, the faster the reaction. So, how did you do on this question? Let me know in the comment section below. Anyway, that's it for this video, guys. Thank you for joining me in the laboratory. Please leave a like on this video if you found it useful, and don't forget to subscribe to the channel so that you don't miss another one. See you soon!